SA571 Compandors by ON Semiconductor. Welcome to the training module on the SA571 Compandor IC from ON Semiconductor. In this session, we will focus on the SA571 features, block diagram, and the various applications it can support. Compandor is the contraction of the two words compressor and expander. There is one basic reason to compress a signal before sending it through a telephone line or recording it on a cassette tape, and that is to process the signal, be it music, speech, or data, so that all parts of it are above the inherent noise floor of the transmission medium, thus avoiding running into the maximum dynamic range limits, causing clipping and distortions. The compressor function processes uncontrolled input signals into controlled output signals. This ensures that distortions caused by a narrow dynamic range medium, such as telephone lines, magnetic tapes, RF and satellite transmissions, are avoided. The expander function allows the user to increase the dynamic range of an incoming compressed signal, such as radio broadcasts. The SA571 is a versatile low-cost dual-gain control circuit in which either channel may be used as a dynamic range compressor or expander. Each channel has a full-wave rectifier to detect the average value of a signal, a linearized temperature-compensated variable gain cell, and an operational amplifier. It is an inexpensive integrated circuit which offers a pair of high-performance gain control circuits featuring low distortion, typically less than 0.1%, high signal-to-noise ratio, about 90 dB, and a wide dynamic range, about 110 dB. This compandor is well suited for use in modems, telephones, cellular radio and radio communication systems, as well as satellite broadcast and receive audio systems. The SA571 Compandor building blocks consist of a full-wave rectifier, a variable gain cell, an op-amp, and a bias system. The full-wave rectifier rectifies the input current which flows from the rectifier input to an internal summing node biased at V reference. The rectified current is averaged on an external filter capacitor tied to the rectifier cap terminal. The average value of the input current controls the gain of the variable gain cell. The gain will thus be proportional to the average value of the input signal for capacitively coupled voltage inputs. Figure 1 shows the concept behind the full-wave averaging rectifier. The input current to the summing node of the op-amp, Vin divided by R1, is supplied by the output of the op-amp. If we can mirror the op-amp's output current into a unipolar current, we will have an ideal rectifier. The output current is averaged by R5 and CR, which set the averaging time constant, and then mirrored with a gain of 2 to become IG, or gain control current. Figure 2 is a diagram of the variable gain cell. This is a linearized two-quadrant transconductance multiplier. Q1, Q2, and the op-amp provide a pre-distorted drive signal for the gain control pair, Q3 and Q4. The gain is controlled by IG, and a current mirror provides the output current. This diagram shows typical performance characteristics illustrating the basic input-output transfer curve for a compressor or expander circuits. Figure 1 shows how the circuit is hooked up to realize an expander. The input signal Vin is applied to the inputs of both the rectifier and the G cell. When the input signal drops by 6 dB, the gain control current will drop by a factor of 2, and so the gain will drop by 6 dB. The output level at Vout will thus drop by 12 dB, giving us the desired 2-to-1 expansion. Figure 2 shows the diagram for a compressor. This is essentially an expander placed in feedback loop of the op-amp. The G cell is set up to provide only AC feedback, so a separate DC feedback loop is provided by the two RDC and CDC. The values of RDC will determine the DC bias at the output of the op-amp. This diagram shows an application of a compandor being used as a limiter in an automatic gain controller or AGC. Typical applications of an AGC are compressors and limiters. Compressors and limiters perform similar tasks, but with one exception. Limiters abruptly limit the signal above a certain level, while compressors control the signal more gently over a wide range. A limiter continuously monitors the signal and intervenes as soon as the level exceeds a user-adjustable threshold, usually from -40 dB to +20 dB. Any signal exceeding this threshold will be immediately returned to the adjusted level. Compressors control the signal more gently over a wide range. A compressor also monitors the input signal continuously and has a certain threshold level like the limiter. With compression, the signals are not reduced abruptly once the threshold has been exceeded, but rather by a ratio of the input range set by the user. This ratio can range from 1:1 up to 20:1. The compressor, like the limiter, has two ways to implement the compression above the threshold: hard and soft knee responses. On semiconductors, current line of compandors can easily be configured as a soft knee compressor with a fixed compression ratio of 1:2. Here is a typical circuit using a compandor as a voltage-controlled attenuator. It uses an external op-amp for better performance and an exponential converter to get a control characteristic of -6 dB per volt. Trim networks are shown to null out distortion, DC shift, and finally to fine trim gain to 0 dB with 0 volt of control voltage. Op-amp A2 and transistors Q1 and Q2 form the exponential converter, generating the exponential gain control current, which is fed into the rectifier. A reference current of 150 microamps, 15 volt divided by R20 of 100 k ohms, is attenuated by a factor of 2 or 6 dB for every volt increase in the control voltage. Capacitor C6 slows down gain changes to 20 milliseconds time constant, so that an abrupt change in the control voltage will produce a smooth sounding gain change. R18 assures that for large control voltages, the circuit will go to full attenuation. The rectifier bias current would normally limit the gain reduction to about 70 dB. R18 draws excess current out of the rectifier. After approximately 50 dB of attenuation at a -6 dB per volt slope, the slope steepens, and attenuation becomes much more rapid until the circuit totally shuts off at 9 volts of control voltage. A1 should be a low noise, high slew rate op-amp. R13 and R14 establish approximately 0 volt bias at A1's output.